Welcome to the EPG Pathshala, the lecture material for the postgraduate program in computer science, and this is the compiler design course. We are on module 29, where we will be discussing about construction of basic blocks from a set of 3 address code, flow graphs and next use information. The objectives of this module are to learn to construct basic blocks and flow graphs, to learn about the possible transformations in basic blocks, and to understand about next use information for application towards register allocation and for final code generation. The basic block is a sequence of consecutive instructions with exactly one entry and one exit point. This we already know. Now basic blocks and control flow graph. Now we know what's a flow graph. Now we will define here what's a control flow graph. It's a directed graph with basic block Bi as vertices, and you define edges from Bi to Bj if and only if Bj can be executed immediately after Bi, or I will put it this way, Bj will be executed immediately after Bi. Okay, if that is your situation, I have an edge from Bi to Bj. Now in this case we already know Bj is called as a successor block and Bi is called as a predecessor block. Now this is irrespective of whether it is a backward arrow or a forward arrow. So from where you originated, that is called as a predecessor block, to where the arrow went, that is called as a successor block. Now the algorithm to partition a basic blocks into create basic block is discussed here. Input will be a sequence of 3 address statement, output will be a list of basic blocks with each 3 address statement in exactly one block. Okay. Determine the set of basic leaders here. The first statement of if basic blocks, the first statement is a leader, okay, and any statement that is going to be following the target of a goto is a leader, and statement that is immediately following a goto is also going to be leader. Now you identify first set of leaders here. After getting the leaders, for each leader its basic block consists of the leader along with all statements up to but not including the next leader of the or the end of the program. Okay. So between two leaders, whatever statements occur, that will be comprising in one basic block, where the first leader and the statements following that will be in that particular basic block. So let us take this example here, where we will have this is a input, production is equal to 0, I equal to 1, prod is equal to prod plus a of I into b of I is equal to I plus 1, and then end, and this is a do while. So while I less than 20. If you convert this to 3 address code, so production is equal to 0, I equal to 1, those two are same. So I have to do an a of I into b of I. So for that I will do T1 is equal to 4 into I, and then T2 is a of T1, T3 is 4 into I, and T4 is b of T3, and then these should basically be multiplied as T5 is equal to T2 into T4, and that should be added to with production, which is T6, and it is assigned back to production. I then increment I, and then I will call I is equal to increment I in a temporary variable, assign it to I. If I is less than or equal to 20, go to this statement 3. Now this is what we are looking at as a 3 address code for this particular example. Now we know that the first statement is a leader, okay, which is the beginning, hence it is a leader, and then the line number 3 is a target of a jump, hence that can also be considered as a leader. So between lines 1 and 3, the statements will be lines 1 and 2, that will form one basic block, and the remaining will form another basic block. Okay. Statement following 12 is a leader, statements 3 to 12 is another basic block. Okay. So that is what we have shown here. So statements from 1 to 2, that will be block B1, which is going to be a leader, and statements from 3 to 12, which will be another leader, and after this 12, whatever will be there, that will form the next basic block. And I have an edge from here to here, which indicates as a control flow, because I have a target jump. So after this I have to go here. This is what basically looks upon as a control flow statement. So I call this as a control flow graph, because after doing this I have to go back to this position. That is what is my indication. And here if I call this as block B1 and this as block B2, I can say B1 is the predecessor of B2 and B2 is the successor of B1. Okay. So this is what we construct, and so here I do not have multiple statements. If I have an if and a go to, if and a else, If I have if else, I will have two statements, right? One is go to L1, other will be go to L2. So that will be another basic block. The statements comprising the body of if will be one basic block. Statements comprising body of else will be another basic block. Okay. Now after that, they will have to merge together to come to the next statement. So that will be shown in subsequent modules. So in addition to that, you can define what is called as a loop. A loop typically looked upon as a collection of basic blocks such that all blocks in the collection are strongly connected. Any node to any other node, there is a path of length one or more within the loop. That is called as strongly connected. Okay. And the collection has a unique entry, and the only way to reach a block in the loop is through that particular entry. So I have a loop which is I am talking with reference to the point of control flow graph, where it can be a strongly connected loop or it could be a weakly connected loop. So strongly connected loop will basically have will be having only one entry point, okay, and to reach all blocks contained in that particular loop, that is the only way to enter. And on addition to that, any node to any other node in that particular loop, there is a path of length one or more within the loop. Okay. So you will have multiple paths within that particular loop. So you call that as a strongly connected loop. And you have what is called as outer loop and inner loop. Loops not containing any other loop is called as inner loop. Obviously, loops containing more than one inner loop can be called as outer loop. So typically, strongly connected loops will basically be outer loops. In this example, the same which we have already looked upon is discussed here. So this is one basic block, second one, third and fourth basic block. Now the strongly connected components are B2, B3 are strongly connected. Okay. So there is more than one way to, there is a path of more than one length 1, and to come to B3, I have to come through B2 only. So B2 and B3 are strongly connected. And one more is B4. Okay, B4 is also strongly connected because I have to come to B4, I have to necessarily come through B2 only. Okay, so that is also connected. So entries are here B3, B4 are entries to B4. So this is one example. We will come back to this with reference to dominators and flow graphs in the next module. Now I have formed basic blocks from my 3 address statements. Now we said that the ultimate reason behind forming basic block is for register allocation and for optimization. So to do optimization, I should know what possibilities are there with reference to basic blocks in terms of transformations. Now transformations can basically be of two types. One is structure preserving transformation, other one is algebraic transformation. Now to know that, a basic block can be thought of as one that computes a set of expressions, and the values of the variables outside the block is termed by the computation that is happening inside the basic block. So whatever you do inside the basic block, that will decide the value of the variable outside the block. So two basic blocks can be thought of as equivalent if they compute the same set of expressions. This is one more information that is required for us to compute. So for example, here let us take this basic block and let us take one more. I have here a value b equal to 0. I will say T1 is equal to a plus b. I will say T2 is equal to c into T1, and I will say a is equal to T2. Okay. Now what does this basically say, translate to? This simply says T1 is equal to a plus b. B is 0, therefore T1 is also got the value only a. I say here T2 is equal to c into T1, which is nothing but c into a, and I will assign a is equal to again c into a, okay, because b is 0. So this statement finally does what is a is equal to c into a, that is one computation, assigning b equal to 0, that is another computation. Now this block and this block are equivalent because here it says a is equal to c into a, and then it simply says b equal to 0. So outside this particular block, the value of a and b are same in both the cases. Therefore we say that these two blocks can be looked upon as equivalent blocks. With that, transformations can basically happen in a idea to improve your code generation in terms of optimization of code, or size of code getting reduced, or speeding up your code. And global transformations are performed across basic blocks. but before that local transformations have to be performed within a particular basic block for optimization. Transformation must be safe and it should preserve the meaning of the code. A local transformation is safe if the transformed basic block is guaranteed to be equivalent to its original form. So, local is safe because you are computing whatever is happening within that and you rearrange your statements or do some manipulations that can be ensured to be semantically correct rather than carrying out across basic blocks, which we will again talk about with reference to optimization later, but your transformations can basically be either local or it could be global. Okay. So, local means within a basic block, global means across basic blocks in a particular control flow graph. Okay. So, the transformations are structure preserving transformations where the syntactic structure of the statements in the basic blocks are not altered. Okay. Syntactic structure is not altered. Algebraic transformations are where the syntactic structure is altered, but it uses the mathematical identity to preserve the semantics. Okay. The first one is structure preserving transformation, where we will have 4 types. One is the common sub-expression elimination, second one is dead code elimination, third one is renaming of temporary variables, fourth one is interchanging of 2 independent adjacent statements. So, this is what we do in case of choice of evaluation order, which we already have seen basically. Okay. So, that we will see with respect to blocks. The first one is common sub-expression elimination. For example, here let us take A is equal to B plus C, B is equal to A minus D, C is equal to B plus C, D is equal to A minus D. Now, let us look at this. So, here A is equal to B plus C, A is equal to A minus D, C is equal to B plus C and D is equal to A minus D. Now, between this statement and this statement, the value of A and D is unaltered. Okay. Between this statement and this statement, statement 2 and statement 4, the value of A and D is unaltered, whereas between the first and the third, value of B has changed. Okay. But both will have the same RHS. So, this is also computing B plus C, this is also computing B plus C, but between B plus C computation here and between the B plus C computation here, value of B has changed here. So, therefore, B plus C cannot be reused. On the other hand, between this computation and this computation of A minus D, value of A and D has not changed. So, therefore, the already computed value B, which is nothing but A minus D, can basically be used here. So, D is equal to B. I can simply do a reassignment here rather than a computation of A minus D. So, this is called as common sub-expression, that is the RHS evaluates to the same expression, and between the evaluations of the first expression and the same expression again, if the values of the RHS has not changed, RHS in the sense that RHS variables has not changed, we can basically reuse the already computed value itself. That is called as common sub-expression identification and elimination. So, how do we eliminate it? Eliminating is reusing the variable which is already assigned with a particular expression's value. So, here I have assigned it to B. So, I am reusing B in place of A minus D. Now, here T1 is equal to B into C, T2 is A minus T1, T3 is B into C. So, again between the computation of T1 and T3, the value of B and C has not changed. So, I can use here T3 is equal to T1 and then use that here, but there is one more thing which I have basically done. T3 equal to T1 is basically meaningless because T3 itself is going to be a temporary variable. So, I have used in place of T1 itself T3 directly. So, because between this statement and this statement, B into C hasn't changed. So, I can replace this with T1. So, T3 equal to T1 is meaningless because T3 itself is going to be a temporary variable, but T1 is already a temporary variable. So, I can reuse that and get it as T4 is equal to T2 plus T1. So, I have eliminated one complete statement of computation right here. Okay. The next one is called as dead code. Whatever we have done earlier in terms of removing this T3 equal to T1, that is actually dead code. Okay. So, we have already incorporated dead code here. So, but anyway, let us look at it from this particular example's point of view. So, B is equal to A plus 1 and A is equal to B plus C. Okay. So, what here we have done is assuming A is dead, that is assuming A is not going to use later, okay, that is after this basic block A is not used at all. In that case, I can get rid of this complete statement as it is. So, I can even I do not even have to look at computing that. So, B is equal to A plus 1 will be your scenario. The second situation is if true, go to L2. Okay. Now, if it is false, it is going to come here. So, this, and supposing you are always going to have a true value, you are never going to have a false value, then you can, this computation is going to be redundant. So, you can basically remove that. So, redundant code is called as dead code, as well as computing a variable which is not going to be used later is also called as dead code. So, removing unused statements, that is dead code, and then renaming temporary variables. This is one more transformation. So, here T1 is equal to B plus C, T2 is equal to A minus T1, and I have said T1 is equal to T1 into D. Okay. So, D is equal to T2 plus T1. So, this can be converted to T3 is equal to T1 into D, okay, and I have used that here. So, I am reusing temporary variable, I am renaming temporary variables here. T1 into D is different from B plus C, right. So, I am not reusing the same variable here, but I am calling it with a T3. So, this is one more possible transformation. So, temporary variables that are dead at the end of a block can safely be renamed. So, this is one more situation, but it is not required in many cases, but still it is a possible syntactic structure preserving transformation. Interchanging of statements. Supposing here I am going to do A minus T1 first and then T1 into D. Okay. Between these two statements, value of T1 is not going to change. Okay. So, what I can do is I can compute T1 into D first, because after this computation what happens, T1 will be in a register. So, when T1 is in a register, I can reuse the register itself directly here to compute T1 into D first, and then I can use the register content itself to do A minus T1. Okay. So, altering these two statements is not going to change your semantics of the particular basic block, therefore, it is possible to change, because that is going to reduce 2 instructions at least, as we have already seen in the previous module. So, here you could change statements if it is not going to be affecting your meaning. So, independent statements can be reordered without interfering one with other. Okay. The next type of transformation is called as algebraic transformation, which uses mathematical identity to perform some equivalence transformations. So, for example, T1 is equal to A minus A. Definitely we know it is going to be 0. So, I can simply say T1 equal to 0 directly here rather than doing a computation here. Then T2 is equal to B plus T1. So, since T1 itself is 0, I can simply call T2 is equal to B. Okay. And then T3 equal to 2 into T2. So, multiplication by 2 is nothing but left shifting by 1 basically. So, I have left shifted T2 by 1, which is nothing but multiplying it by 2. So, that is one more this is actually a cheaper operation compared to multiplication. Okay. And then I have here x is equal to y power 2, y squared. Y squared is nothing but y into y. So, I am using that here. Okay. Similarly, I can also say if it is going to be y into 0, I can say it is nothing but 0. I can assign the value as 0 itself. If I am going to say y into 1, I can assign the value as y itself. So, depending upon the properties of mathematical identities, I can use some transformation which is possible here. Then after that, we come to an important topic called as next use information. This is needed for dead code elimination and for register assignment. It is computed by a backward scan of a basic block and performing the following actions on every statement. So, you start from the last basic block's last statement and move all the way upwards to your, all the way up to your first statement of the first basic block. Supposing you have a statement number I in which you have x is equal to y operator z. You have to have two information, one is called as liveness, other one is called as next use. So, in that case what you do is you add liveness or next use info on x comma y and z to statement I, set x to not live and no next use. So, LHS variable is said to have no next use and it is not living, and you set y comma z to live and their next use is at line number I. Okay. It is a backward scan. So, but I will be scanning from the top to get my code generated. So, I will be looking at the next previous level to say that where y and z is going to be used. So, you say that y and z will be used at line I. So, you call the next use of y and z as I, and then you set y and z to live at this particular point I, okay, because it is required to compute x is equal to y plus z. So, this is a small algorithm. Based on that, let us take this example. This is as given in the textbook itself. So, I have two line numbers I and j. I is the first line number and then I will have a line number called as j, for example, say. So, to start with, you attach current liveness or next use information to the line numbers, to the variables. As the info is empty, you have to assume all variables are going to living. Okay. So, here live of A is true, live of B is true, live of T is also true, and then you say next use of A is none, next use of B is also none, next use of T is also none, before looking at line J to start with. Then what you do is, you are encountering line J. At this point what happens? You should say T is supposed to having no life and no next use, okay, and then you have to say A and B is left next use is at line J and A and B will be living at line A. That is what the algorithm says. So, here live of A is true, live of B is true, live of T is false, next use of T is also none, and next use of A and B is at line number J. That is what you basically know. Okay. Now, this is at the last statement. After that, I will encounter statement I. Okay. So, what is the first information at line I? I have to attach current information to all the variables. So, this is basically copied as it is here. Okay. And then what I do, as you could see, live of A is true, live of B is true, live of C is false because I do not know, similar to the base condition set. Next use of A is J, next use of B is also J. Now, after next use of C is none. Now, what we should do basically, next use of A should be, A is not supposed to live here, okay, and you should take that off, and B and C will be having a next use at line number I is what we have to basically attach. So, we say live of A is false, which was true earlier, okay, here, live of B is true, live of C is true, next use of B is I, next use of C is I, okay. Now, look at this, live of T is false and next use of T is none because that is what is available in the previous situation. Now, what I have to do is, I am doing a forward scan. When I am encountering this particular line, what I will know is B plus C, out of B plus C, they are used at line number I. After finishing I will be looking at this statement, okay. So, B will have a next use at line number J, A will have a next use at line number J, So, if A is in a register, I will not remove from it. If B is in a register, I will not remove it from that, okay. So, this will be available before looking at line number I. So, supposing B is already in a register here, I will avoid instructions to move B to a register or C to a register because they have to be in a register for computation here and they are required at line number I. So, I will have this information before looking at line number I itself, therefore, it is going to be useful, okay. So, this next use information is going to be required for us to generate optimized code as well as optimized register allocation for our situation. So, it does a backward scan from the last line towards the first line and you will assign to it, it is a two-step procedure. First one is attaching current information directly to all the variables, and then second step will be LHS variable is said to have no life and no next use. RHS variables is said to have liveness and next use will be at the corresponding line number which you are encountering now, okay. So, you assign, but your code is generated in top down fashion. So, when you look at this particular point, before even looking at I, if B is in a register, I know that B is required at line number I, therefore, I will not remove B from the register. So, this is going to be useful for looking at the number of instructions in a correct fashion as well as checking out unnecessarily swapping between to and fro from register, that is also prevented by this particular information. So, to summarize this module, we have done conversion of code to basic blocks, constructed that control flow graph also. We have also looked at the possible transformations in basic blocks with respect to structure preserving transformations and algebraic transformation. We have also looked at next use computation for register allocation and code optimization. Thank you.